Hi, I'm Gonzalo Palma from the University of Chile, and this talk will be about loops in de Sitter spacetimes. So let me start with basic aspects about the four-dimensional de Sitter spacetimes. First of all, you can visualize for the de Sitter spacetime as a surface in a five-dimensional Minkowski spacetime. The surface is parameterized by that equation. And you can see by eye that the spacetime is invariant under 5D boosts and rotations. And these are the so-called de Sitter isometries. You can slice the spacetime with the so-called cosmological coordinates, which are given by those relations. And the scale factor I'm going to work with is given by that form in conformal time. And that implies that the 4D de Sitter spacetime is parameterized by that metric. Given any 2 points x and x prime, you can join them with a geodesic, and the geodesic distance is going to be given by that expression, where q acquires that form in terms of cosmological coordinates. And it happens that q is de Sitter invariant. That means that it's invariant under de Sitter transformations we just saw in the previous slide. In the particular case where these 2 points are on the same time surface, this quantity q acquires that form. In addition, if you have a fluctuation f, then it is useful to consider the Fourier transform of these fluctuations, which is going to be given by that expression over there. And that implies that in cosmological coordinates, the wavelength of fluctuations is going to be stretched as time passes, simply because they are proportional to the scale factor as it is shown there. If you have a fluctuation in a given time tau, for example, you will have some wavelength. And later on, if you study the evolution of this fluctuation, you will discover that the wavelengths are longer, of course. And eventually they will become super horizon. That means that their value is going to be larger than the Hubble radius, which in terms of k and tau, it means this particular limit over there. And we are going to study the computation of correlation functions in this limit. So let's move on to discuss the computation of correlation functions in de Sitter. Consider the following massless scalar field theory with a given potential, which introduces interactions for this field. And you can work with a Schwinger-Keldysh formalism, which allows you to compute correlation functions with the help of Feynman diagrams. So for this, it is useful to expand the potential in this form where you have these coefficients lambda n. And in the Schwinger-Keldysh formalism, you will find out that the degrees of freedoms are doubled. And this means that a given coupling lambda will imply two vertices, a black and a white vertex. And you will therefore have many propagators joining these different types of vertices. And of course, you will also have what are called bulk to boundary propagators, which joins the vertices with the time surface at which you want to evaluate correlation functions. There are two important considerations here. One of them is that each vertex introduces a time integral of that form. These integrals are usually quite complicated. And certain propagators, especially those joining vertices of the same color, comes with Heaviside functions, which implies nested integrals. And this is an additional complication in the computation of correlation functions. So to compute a given endpoint function, you just need to put together these rules, and you will have different contributions coming from different vertices. So here you have, for example, single vertex diagrams and two vertex diagrams, but you have, of course, every possible combination. And you can even consider the inclusion of loops. All of these objects are going to be quite complicated if you want to get analytical expressions. The simplest example is given by a diagram with a single vertex. The complex conjugate is going to be the same diagram, but with the opposite vertex, with a white vertex in this case. And both two boundary propagators are going to have that form. You have to also remember to integrate, and the results are going to be of this form. So this is the contribution to an endpoint function coming from a single vertex. And you can see that the appearance of a logarithm, which can be explained from the fact of various cancellations and the reduction of the integral into that expression over there. Another example is a two-vertex diagram. This is a slightly more complicated, but it can be worked out nevertheless. And you will find this form for the result. And you can see also the appearance of logarithms in the soft moment limit. So the purpose of this talk is to discuss the role of loops in the computation of correlation functions. And to begin with, I would like to review three important claims that you can find in the literature. So the first statement I want to review was made by Bruce Allen in a famous paper from the 80s. and it consists in the following. If you try to work with a massless scalar field in the de Sitter spacetimes, you will find it impossible to define a normalizable vacuum state, which is invariant under the de Sitter isometries. The second claim is related to the first one, and it consists in the following statement. Loop corrections must be regularized using moving cutoffs in the IR, and this choice actually ensures the explicit breaking of the de Sitter invariance. And actually, this choice introduces the appearance of secular growth. The third claim is that the stochastic approach introduced by Starobinsky and Yokoyama provides an unperturbative method to resume secular growth coming from loops. So let me look into details all of these three claims, and let's start with the first one. So let's say that you want to compute a two-point correlation function in the simplest possible scenario, free massless scalar field theory. Then that's your theory over there, and you will need to quantize this scalar field. You just do it in the conventional way, and then the two-point correlation function is going to be given by that expression. I will choose to work with mode functions, which are Bunch-Davies, just for simplicity. If you replace this mode function in the integral, then this is what you get. It's just an integral with a sinusoidal function. So let's deal with this function. This is what we have to integrate. And if you just plug it in Mathematica, this is the result that you will find. So you can see the appearance of this de Sitter invariant function Q, which I remind you is given by that expression. But you can also see the appearance of this logarithm of the scale factor A of tau. In addition, you have a constant there, which is divergent, which is given by that specific limit. So in the famous paper by Bruce Allen, this result was interpreted as a spontaneous symmetry breaking of the de Sitter symmetries. So that's it for this first claim. Let us now check the second claim. So in dealing with this integral from the previous slide, we saw that the lower limit leads to a divergence, and we can just avoid it by working with a moving cutoff, replacing this lower limit. And in this case, direct integration gives you exactly the same result as before. So this is a way to just avoid divergences. Why is this step important? Well, it's because if you are computing endpoint correlation functions, you already know that the tree-level diagram contains already logarithms of this form. We discussed this previously. But also, if you consider loops, then direct computation shows you that loops are proportional to two-point correlation functions at coincident points. This is just the outcome of the computation. And given that you already know that these two-point functions brings secular growth, then the appearance of loops in diagrams will also come together with secular growth. So for example, this correction there will have not only one logarithm, but it will have a second logarithm that breaks the de Sitter isometries. If you have more loops into consideration, then this is actually enhanced. So for example, you will have powers of this secular growth in the way shown in this slide. So that's it for this second statement. And now let us review the third one. So imagine yourself at pure de Sitter. And as we discussed before, there must exist a maximum wavelength, which is given by this co-moving cutoff in the IR. And there must exist a time, tau naught, at which this wavelength was of the order of the Hubble radius, as shown in the figure. Next, let's see what happened with the evolution of this system. As time passes, this fluctuation evolves and the wavelength stretches. And later on, it will have some size L of tau, which is just given by the previous wavelength multiplied by the scale factor of the new time. Of course, the Hubble radius is just a constant, and it is still there. It's an important size of the system. And if we focus on only superhorizon modes, then we will have a collection of fluctuations with wavelengths ranging from the size of the Hubble radius up to the longest wavelength possible, which was the initial fluctuation. So what can we do now? We could, for example, compute cumulants, and cumulants will have information about the statistics of the system. In this case, cumulants are just the integration in momentum space of correlation functions ranging from the lowest wavelength up to the highest wavelength, as it is shown there in the figure. If you replace the previous integral with the correlation functions that we discussed before, then this is the result that you will find, where sigma squared is given by this expression, which encodes the secular growth that we have been discussing. And you can see, this is very important, that there is a sum in L, which stands for loops. And so that's the way that loops contribute to the secular growth of cumulants. Furthermore, you can use these cumulants to actually compute the probability density function describing the statistic of the system. And for this, you just need this formula. This is just a mathematical fact. And so if you plug in these cumulants in that expression, then you will find that the probability density function respects a certain equation, which is precisely the Fokker-Planck equation found by Starobinsky and Yokoyama during the 90s. And this result shows actually the connection between loops, secular growth, and the stochastic formalism by Starobinsky and Yokoyama. This is not exactly the same computation that Samis and Woodard performed in their famous paper, but is precisely equivalent. And what matters here is that it displays the connection between loops, secular growth, and the stochastic formalism. So that's it for the third statement that I wanted to review. But now, in the rest of the talk, I would like to present some objections to this picture. So let me start by objecting the first vertex of this triangle. So here you have again the result by Allen, where you see the appearance of the secular growth plus this divergent term C infinity, which depends on that limit of the comoving momenta that appears there. Now there is a cut. In fact, comoving momenta is not invariant under de Sitter transformations, and this means that this constant is actually not a proper constant. In a way, it hides some dependence on the spacetime coordinates. How can that be? Well, let's give a step back and let's do something very simple to this integral. Let's just do a change of variables. Instead of working with k, let's integrate on this new variable p, which is just proportional to k in that form. Yeah. So if you perform that change of variables, then this is the integral that you will find. This is just a result of that change of variables. And you can see that now the integral depends explicitly on q. Yeah, and it is only a function of q, this is invariant quantity that I showed before. In fact, if you now integrate directly, just plug in this in Mathematica, this is the result you get. You see that there is no secular growth whatsoever. And now this constant C corresponds to this other limit. Okay, so this looks suspicious because this is just the result of a change of variables. How can we decide which procedure is the correct one? So in fact, there is a method, and this is just dimensional regularization. So let's give a step back and write down the two-point correlation function in d dimensions. And this is the expression that you get for a general d dimension. And if you now directly solve this integral, this is what you find. And you can see that, again, is a function only of q, the de Sitter invariant variable. Now you need to perform the limit d going back to 3, which is the number of spatial dimensions. And by doing so, you find this result, which coincides with the previous result, which happens as a result of the change of variables. In this case, the divergent constant is just proportional to 1 over d minus 3, as is normally the case in dimensional regularization, plus finite terms, which appears due to the method. So you can see there is no secular growth. And in fact, this result means that the two-point function at coincident point is just a constant. So in my opinion, this result reveals that there is a misunderstanding about the non-existence of normalizable vacuum states invariant under de Sitter isometries. If you work with a massless scalar field, well, your vacuum state will be non-normalizable. That means that you will have some divergences. You have to deal with them. But that doesn't mean that the de Sitter isometries are going to be broken. So let me now scrutinize the next statement, which is about loops and the use of comoving cutoffs. So let's briefly examine what happened with contributing one vertex diagrams. So here you have the tree-level contribution, but you already know that there will be one loop contributions. And as we just discussed, as we just learned, this one loop has to be a constant because a loop is just proportional to two-point function at coincident point. This is a divergent contribution, and we have to deal with it. And to deal with it, we can just use counter terms, which with the right balance will cancel the divergence coming from this single loop. And in fact, you can do this up to an arbitrary number of loops. You can eliminate divergences order by order with counter terms. And the final result is that one vertex diagrams, independently of the number of loops, are indistinguishable from a tree-level diagram with an effective coupling resulting from this renormalization procedure. So the statement here is that daisy loops, that means loops starting and ending at the same vertex, are in fact indistinguishable from tree-level effects. Okay, daisy loops are actually trivial because they don't have external momentum running through them. What about more complicated loops? There you have an example. That's a horrendously complicated loop to integrate. Well, in fact, we have shown in a recent paper, it's not out yet, but will be very soon in the archive, uh, that these loops are proportional to logarithms of that form, where you have tau multiplied by a function of the momenta, and to the power of v, the number of vertices that the loop that the diagram contains. And you can see that there is no scalar growth in this in this result. So in fact, loops do not alter the appearances of logarithm that appear at tree level. That's the result. I cannot enter into details here, but that's the result that will be out very soon. So that's it for this second claim. I just argue that you don't need to use moving cutoffs and that you can just deal with loops directly with dimensional regularization. And that's the method that we should try to use, even to deal with IR divergences. So to finish this talk, let me revisit the last claim. First, recall that when we discussed the stochastic picture, we assumed the existence of a maximum size, setting the maximum wavelength possible for fluctuations, as it is shown in this picture. And in fact, let me adopt that assumption again, that there is such a maximum wavelength. This could be, for example, due to the fact that in some cosmology, the jitter, that's it, inflation, could have been preceded by another epoch, for example, a radiation-dominated era. In such a scenario, well, this fluctuation will be stretched due to the expansion, and eventually it will become a super horizon, and it will just be too large to be even perceived. According to the stochastic formalism, in fact, fluctuations of maximum wavelength should be highly nonlinear and reach equilibrium. So the interesting question really is what happens with fluctuations of much shorter wavelengths way smaller than this maximum size that we were initially considering. These fluctuations, of course, are stretched also thanks to the expansion. And at a given time, we could ask, for example, what's the statistics of a collection of these fluctuations, ranging from the Hubble radius up to that size that you can see there. So remember that the longest wavelength in this patch are far away from this boundary set by the longest possible wavelength. So if we compute cumulants for this set of fluctuations, you will find this result for the cumulants. And you can see that this result is actually independent of the number of loops. So why is this the case? So the explanation is very simple. For this wavelength, the maximum size is completely out of reach. So these fluctuations just feel that they are in pure de Sitter, and there is no broken de Sitter isometries. And whenever you compute loops, you just do it in the way that I showed you recently. That's it. You just use dimensional regularization, and this is the result that you get. So what can you do with these cumulants? Well, as we did before, we can compute the PDF describing the statistic of the fluctuations. And then we can study the evolution of these. And the evolution is dictated by this Fokker-Planck equation. And you can see that this result differs greatly from the result found by Starowinsky and Yokoyama. Nevertheless, I would like to advertise a result that you can find in the following paper. And this is the fact that in the renal derivation by Starowinsky, there is an assumption that is equivalent to regulate loops with moving IR cutoffs. So if you're not regulating loops with IR moving cutoffs, then you get a different result. And this is the result I just shown. So we're not really saying that the stochastic formalism is wrong. We are just saying that one has to revisit the stochastic formalism with some care. And so our proposal is that there might be some important effects that the stochastic formalism in its current form is missing. And these are perturbative effects that one has to take into account, and they might be quite important. So these are my conclusions. I think I have presented some important objections to standard claims regarding the computation of correlation functions in de Sitter. I have argued that there is no spontaneous de Sitter symmetry breaking for massless scalar field theories. There is no scalar growth coming from loops, and the stochastic picture needs some refinement. Thank you very much for watching this video.